Okay, here we are once again. So before we get started with any new stuff, are there any questions so far on anything that's been presented? And what about the homeworks that are due today? Did we draw a line under those last time? Or did we already have some for next week?
I don't think we have anything for next week yet.
Good, good. Okay, so I'll pick up where we left off. And where we left off was with motion with constant acceleration. So this is stuff you learned in Physics 4A, and it's going to represent the limiting case of a lot of things we do. So this is something we have to know very well. Constant acceleration. And what we had was the second derivative of the position with respect to time is equal to that acceleration, and we're calling that a constant vector. So because it's a vector, it actually has three components. So this is in Cartesian coordinates b squared x dt squared equals a sub x, and same for y and z. B squared z dt squared equals a sub z. Well, what we did was we just took this one because they're all going to be the same. Okay, so we had this, and of course we also had v is equal to r dt, same argument, three equations, and that's why this case is so easy to integrate up. Okay. It's really just the antiderivative. This one gave us, if you have this in your notes already, it gave us b equals b naught plus a times t, and this one gave us x equals x0 plus v0 t plus 1/2 a t squared. And you would have that for all three components, so it's good enough to have it for one. And then because of that, I was able to say, good, r is equal to r0 plus v0 t plus vector a over 2 t squared. And you know, you should take the derivatives of these and make sure you get back the original thing. You take the derivative with respect to t, and you kill this one, you end up with v naught, 2 cancels, you get a times t, right? And take the second derivative, you get a equals constant. Okay, so this is a really nice and important result. Now the homework was to show that this motion will be restricted to a plane. And I'm just going to tell you the argument for it, and you guys should, you know, carefully write it out this time. The argument is that you can take r sub 0 as the origin without any loss of generality. Okay? Or you could look at r minus r sub 0. If you do that, the right-hand side is spanned by two vectors. Right? You have the vector v sub 0, the vector a. So at most they span a plane. If they're parallel, of course, then the motion's restricted to a line. But so the argument on this problem, you know, before you get into any fancier ideas, is just that v naught and a are vectors. Vectors span a plane. So now the motion is restricted to a plane. So at this point, so I'll just write here, we find that motion, the motion is restricted to a plane. And at this point, we can then talk about projectile motion. That'll be the next thing. Plane. So it's motion in 2 dimensions, and now we can do projectile motion. Projectiles. Okay. And now for the projectiles, we can start to specify things. We often use the XY plane. Okay, or the XZ, but XY is good enough. And what's the direction of gravity in here? Gravity points down. Therefore, the acceleration, A, is equal to minus G J hat, if you want to look at it that way. You guys are familiar with X, I, J, K hat. And equivalently, we could say 0 minus G 0 if we wanted to have an ordered triple. We're equally comfortable with all these things, or we will be. So what we do now is launch a projectile from some point y sub 0. You know, we could have it at some point x sub 0, but we'll go ahead and just put it at some point y sub 0 here at the origin of the x-axis. We launch with a certain initial speed at a certain angle above the horizontal, and then we just let her rip, right? We're going to get some motion that looks like that. So we have everything in place to specify exactly what happens now. So the acceleration is only in the y direction. If we go back to this general expression here, for x, we have no acceleration in the y direction. So what we have here, x is just equal to x0 plus v0 x t. We could have actually taken that off here as well. No y direction component, x0 plus v0 x t. The motion in y, it's got the initial condition y sub 0. Now we have the whole thing. Just take the y component of this equation, v sub 0 y t, and then the acceleration, 1/2, we've got the minus sign, because of the down being the positive direction, minus 1/2 g t squared. So yeah, that's everything right there. You know, it's restricted to a plane, so we didn't have to have another coordinate. You guys recognize those expressions? Yeah, hopefully. All right. You've seen those before. What about the shape of this trajectory here? We've been told it's a parabola, so we're going to prove that again. We've got a little room here to work with. So what we have to do is say something about these components, v sub 0 x, v sub 0 y. V sub 0 is a vector directed as shown here. So we'll just add here with v0 x equals v0 cosine of angle theta, v0 y, v0 sine the angle theta. So now we really have everything with which we can answer any kind of question. You know, where is this projectile at any point in time? How fast is it going at any point in time? How far will it go? And so forth. So I will solve a couple of those and I'll assign a couple of those. And let's see. First of all, we'll do the trajectory. This generates a pretty complicated formula, but what we're going to do is just solve for t in this equation and plug it into this second equation. So what we get is the following. We take t equals, and you know, we're gonna let x naught is equal to 0, just for the record, right? X naught is equal to 0, so t is just x divided by b0x. And we take that into the y equation. Get y equals, keep the y sub 0, we can ditch that later as well, plus b0y. And since I have the t right here, x divided by b0x, and minus 1/2. We will have g in the numerator, and the t has to be squared, so x squared over b0x squared. I'm gonna do one more step on this thing. So this is where the formulas start looking complicated, and there's a way to make them look simpler. Okay. And that is the following. Just a factor off, so we've got y sub 0. So we're going to take the b sub 0 y divided by b sub 0 x. If we look at those over here, divide this bottom one by the top one, we see the b0's cancel, sine over cosine. So we actually just have tangent of theta, so plus tan theta, I'm going to put parentheses around that, times x. Then we have minus g, yeah, let's do this. So we'll take the 1/2 here. Then that factor will be g over b naught x squared. Now this one's kind of a mess. G over b naught squared cosine squared theta. But we're going to go ahead and write it out that way. G b naught squared cosine squared theta. And then we have x squared. Okay, put a box around that. Point at it for a bit. Okay. What is the shape of the trajectory? Good. Shape of the trajectory. Nicer. So the way to make this look much simpler in your mind, because it's overladen with complicated stuff, you just think of that as y become constant. You know, you've got constant times x minus a constant times x squared. Okay. So in your mind's eye, you can say, well, really, I just have y equals y naught plus ax minus bx squared. And if you look at it in that way, yeah, you say, good. It's going up linearly, going down quadratically, that's a parabola, right? On the other hand, since we're physicists, all these things here carry a lot of meaning, okay? And we can learn to analyze the shape of this curve, the one that I just drew here, by imagining the different things that can happen with these parameters. For example, what if this B naught is very, very large? Just imagine a really much larger initial speed of the projectile. Well, that's going to make this entire factor smaller, and that means this thing's going to go a lot farther before it, starts coming down. So this will flatten out the trajectory, so to speak. And also these various angles, or not various, this angle and these various functions here. Tangent of theta, of course, is just going to be the steepness of the initial thing here. So the assignment that goes with this, so once you get used to playing around with these, and always remember, we just got it off of this base, plug one thing into the other, is the range of the projectile. You guys remember that? Somewhere in the distant past, the calculation of the range of the projectile. And I'm gonna assign it for homework. Of course, you can find it everywhere, it's standard material, but you wanna think it through. All of these things will be good in the recitation. Well, actually, this class doesn't have the recitation. Doesn't matter. I'm opening up the recitation to any problems from this class as well. If you guys are interested in that. But yeah, so let's call this a homework problem right now. Let y sub 0 equals 0, you know, and that means we're launching from here, and then calculate the range, we'll call it capital R, the distance projectile flies. Okay? Calculate R, the range of the projectile. And then there are a bunch of interesting discoveries to be made. Because, for example, you'll find that the maximum range is when theta is 45 degrees. And that there are complementary angles, so there are two solutions for each distance. If you're not at 45 degrees, so show maximum R at theta equals 45 degrees. And I'll just write here, prove complementary angles. Complementary angles, theta 1 plus theta 2 equals 90 degrees, have the same range. By the way, one thing I can recommend for you guys is, now that you're upper division, if you can ever get jobs or work tutoring physics for the lower classes, that gives you so much practice in these things. Very good. And those opportunities arise here because we have physics 2A classes. A lot of times students need a tutor. Anyway, that's a good homework problem to get started, have something for next week. And yeah, before we move on, how much of this do you guys remember so far? Jogging the memory, range projectile. This, I'll tell you why this is so important. So this is projectile motion, constant acceleration. Remember I demonstrated free fall. It's projectiles without friction. So free fall projectiles with friction becomes much, much more complicated. And we're going to learn to tackle some of those differential equations with friction that I doubt you've seen before. This you've seen. Thing is, suppose I solve the problem with friction, complicated solution, and I let the frictional coefficient go to 0. What's my answer going to look like? I solve a complicated problem, you know, it's got friction, it's no longer a parabola. But in my answer, I've got a frictional coefficient, name it K or something, right? And I let that coefficient go to 0. What's going to happen to the solution?
It'll look more like a parabola.
It will go back to exactly these solutions. So we have to know these really well because there's a limiting case for a lot of work that we're going to be doing. Okay? And that's one of the major methods of physics really, is to solve something more involved and make sure you get that limiting case back. And then if the friction's small, you can take the limiting case and maybe add a little term to it. So there's a lot of stuff along those lines. Good, so at least this, the other thing is, for this homework problem, and generally speaking, you should include this development. Because I gave, you know, it's already there. You include this development in the solution that you turn in. Because that way you'll rewrite it one more time, and it'll fix it in your memory better. And this is the kind of thing you'll see very often. Good, so that's a review, so to speak. And what I want to do now is the horizontal projectile. as an interesting limiting case. I could leave some of this stuff on the board. Actually, suppose we have a horizontal throw. What's the tangent of theta if we launch horizontally?
Oh, theta is 0, right?
Theta 0. Tangent of 0.
Well, tangent is sine theta over cos theta, right? So it would be 0.
It's also 0. So the horizontal throw, this term is gone. Cosine of 0 is 1. Okay. So the horizontal throw is kind of just what you'd expect. We're going to analyze it. You know, we're going to start here at y sub 0 and launch horizontally, and it falls down. It also has a range, but this range formula that I asked for on the homework won't get you the horizontal range because we're starting from the ground on this formula. And here we're thinking of starting from a bit higher. Okay? This would be like the pitch that a baseball pitcher makes from the mound. If he releases perfectly horizontal, it falls eventually to the ground. So good. Let's see. We'll erase this stuff over here. Actually, I'm going to erase this one and retain these right here. Horizontal launch. So, horizontal launch. And instead of taking the finished result there, I'm just going to go back to these, okay? Horizontal launch, we have v sub 0x. I can just call it v sub 0 now. V sub 0y. 0 because it's perfectly horizontal. There's our picture here. We'll go ahead and call this H. Y sub 0. We'll call H. We know we're just going to launch it out. It'll hit back there somewhere. What do our formulas tell us now? So now we have x equals v0t. Y equals h minus 1/2 gt squared. Okay, so that's the simplified version. And here we see very explicitly that y and x there's an independence of x and y that we want to explore a little more here. Okay. In particular, the height and therefore the time it takes to hit the ground is independent of the launch speed. That's a really key point. The height is independent of the launch speed. So t, I'll call it time that we're in the air is just equal to 2h over g square root. See, explicitly there, it's independent of how fast I throw it. That seems counterintuitive sometimes, but it's a really important fact. You know, if you were to fire a projectile horizontally, say a gun, and drop a bullet at this very same instant, they would both hit the ground at the same time. One at your feet and one way downrange. Okay? So that's a key point. So I'm going to make sure we note that. T air independent of V naught. So what happens if I launch with twice the speed? So here was V naught. This was D. What if I launch with twice the speed? How far does it fly before it hits the ground. Twice the initial speed,
Twice distance.
twice the distance. We keep going, 3, 4, 10, right? So twice the initial speed, exactly twice the distance, in the absence of air resistance, of course. 2e. So this was e naught, this one here is 2e naught. And I'm just gonna write et cetera. Yeah, so what happens if you do this realistically and the Earth is not an infinite plane?
Curvature of the earth would eventually, play a role.
Yeah, well, in fact, if we get exactly the right speed, the curvature of this initial parabola is going to be the same curvature of the Earth, and we will have an orbit. We'll have a orbiting satellite. So that's an interesting progression. Pardon?
What if you fell towards the ground and missed?
Well, then you weren't fast enough. If you're too fast, you're gonna launch into a different orbit. If you're much too fast, you're actually gonna leave Earth and never come back, okay? So there's a really interesting picture in one of Isaac Newton's early editions of one of his books where they actually show that, and there's the Earth with a mountain and a cannon on top, and it shows horizontal cannon launches and the different trajectories they take, and the one that actually orbits the entire Earth. So that's something interesting to look up, but that's the idea we're going to pursue now. Okay? We do a horizontal launch, we do it with exactly the right speed. This curvature matches Earth's curvature, and we're in orbit because it's a perfect sphere. We're above the atmosphere where there's no atmosphere, and that's free fall. In fact, that's the meaning of free fall, is just having the perfect orbital speed. So good, let's erase this here. But you see that comes because of this independence from V0. Now you wouldn't have this independence of these two quantities if there were any kind of friction. Then it's a whole other ball game. Nice development, so words here. So since Earth is not flat, a certain V0 has the trajectory that matches the Earth's curvature. That's what we're going to write here. So a certain launch, right? V0 launch, I'll call it, has a trajectory that matches Earth's curvature. And that's going to give us near Earth orbit. So there's a really good construction for this. Always make these circles large enough. So the construction is as follows. We now take this circle of radius R, and we're going to launch from H horizontally. And the picture now is that we launch with just the correct speed so that we can orbit the Earth entirely. Because we're always falling. Right? When we make it to a certain point here on this curve, we're still parallel to the Earth, no friction, we haven't lost any speed, so we just keep going around. Now, the construction for this, and by the way, that picture I told you, if you search Newton's mountain or Newton's cannon on a mountain or something like that, you'll actually find that picture. It'll come up in your search. So there, there's a mountain with a cannon on it, and actually not a bad idea. They show a number of different trajectories, right? And then this last one makes it all the way around. So there's a calculation that goes with this. And now that you see the concept, I can make it a little bit smaller. The idea is this: we're close to the surface of Earth. So the Pythagorean theorem will work. I'm going to ignore the finite height above the surface, right? And I've got I'm going to use lowercase r for a reason here. I've got L, and I've got this little h here. This is the amount that I fall each time I move forward. Let's see, do I have enough room here? Well, we'll do this. So we have, by the Pythagorean theorem, we have r squared plus L squared equals r plus h quantity squared equals r squared plus 2rh plus h squared. And so we can get rid of an r squared here. We're going to have L is equal to root 2rh plus h squared. So now when I show this to beginners or non-physicists, I'll just wave away the h squared because it's so small. But we don't have to do that. We can actually take a limit. We can take a proper limit and see what happens here. Go ahead and give ourselves a little more room. Because what we have here, I'm going to add this to the mix so it's on down here. We have h equals 1/2 g t squared, because that's just the law of free fall. So when we get out to a certain distance, we've fallen exactly that much. And so this is what we're going to plug in here. So we have L equals square root 2r, and r is a constant, remember, radius of the earth, g t squared over 2 plus, this one's going to cause us no problem at all, 1/2 g t squared squared. The orbit is going to be the limit of L over T as T goes to 0. What do you guys think of that? L is the distance forward. T is the time it takes to fall that little bit. Everybody accept this? That's the speed, right? L over T. I don't even have to do a derivative. I could also say dl dt, but this is the definition of that. And we already have the 2 canceled. When I divide by t, I bring it into the square root as a t squared. That's going to cancel this. So I'm just going to get rg. Over here, I'm going to have 1/2 g t, a quantity squared, because I got rid of 2 powers of t. See, by dividing by t under that square root. And now if I take the limit t goes to 0, this goes away, this remains. So it's equal to the root of r times g. And the reason I did a lowercase r, because I started with the idea of orbiting the Earth, but this is actually completely general. This is a picture on the board. There's no Earth in there. So we actually have a more general or, comma, for uniform circular motion. We could just say V is uniform circular motion, comma, radius R. B is equal to root R times A. So I'm taking a couple steps there, right? I started with the idea of free fall in G, but if I generalize this, it's just V is equal to the root of the radius of the orbit times the acceleration. And that's the acceleration towards the center, just as G was the acceleration towards the center of Earth. Where A equals acceleration towards the center. So I'm going to add a couple little things to the homework for you guys just to calculate, just to know this really. So one thing will be is to find the near Earth orbital speed. Orbital speed. So that's what all these near Earth satellites, low orbit, 100 kilometers, whatever that's close, have. And in that case, you need to plug in the radius of Earth and 9.8 meters per second. It's somewhat less than 8,000 meters per second. Okay. But yeah, then you plug it in, you know it. This formula here, though, you guys recognize this from 4A? It's usually not put in that form. Okay. So I'll get time down.
Question.
Yes.
Regarding the near Earth orbital speed, do we need to add those 100 kilometers to the radius of Earth?
For the exact amount, but since they're so much smaller than the radius of Earth, it's good enough just to put the radius of Earth in, because it gives us a good figure. Yeah. Just use the radius of Earth. In fact, if you're interested though, you could use the radius of Earth and then calculate that and calculate with the added 100 kilometers and see what the difference is. That would always be interesting to know as well. So yeah, I'm gonna reveal this formula to you guys. It's kind of neat. So if we take this expression that we just derived, B equals root RA implies B squared over R is equal to A, right? I just square both sides and divide by R. And this is the one you guys remember from Physics 4A, the centripetal acceleration formula. Okay. So we just did a reasonably rigorous derivation of the centripetal acceleration formula. We weren't even trying, okay? And we got that. So the centripetal acceleration formula. And I can tie this together with one more thing. Sort of as an added result. Recall that we had the calculation, this is in your notes. Oh, no, it's not. This is in the notes of the math methods class. Doesn't matter. I'm going to repeat a math methods calculation. So good, we have the centripetal acceleration formula, very important, right? And we can tie that into our mechanics now. Yeah, I gotta keep track of which of these two classes gets what. Okay. So there we have our derivation, took the limit. If you did DL, if you did the derivative of L with respect to T, it would just be more complicated for the same exam, the same result. circle R as shown below. So what I'm doing here, how many of you guys are in the math? Is everybody here in the math methods course? That's right, only Sam isn't. You're not either. That's all right. I'm gonna repeat this, it's worth it. So you have this circle, and you put it in the XY plane like this. And then you imagine you have a curve that just comes in here and nests with exactly that circle. That means it has the exact radius of curvature at the origin, okay? So this is what we did there. I think we can pull this off again and to make the connection with the kinematics there. So what we found was that we had x squared plus y minus r squared equals r squared. We solved for y, and we took the minus sign. We took r minus root r squared minus x squared. So actually, skip steps. We solved for y, okay? Took the minus sign because it's the bottom half of the circle. And then we took two derivatives. So dy dx is equal to minus 1/2 root r squared minus x squared negative 2x. So that was equal to x over root r squared minus x squared. And then we took a second derivative, and we got 1 over root r squared minus x squared. And the second part we do is no big deal, plus x negative 1/2 r squared minus x squared to the 3/2 denominator negative 2x. We don't even have to mess with this one because we're going to evaluate it at x equals 0. So evaluate it at x equals 0, this complicated one vanishes and we're left with 1 over r. So d squared y dx squared is equal to 1 over r. And that's the meaning of the second derivative at a local minimum. It's the curvature, okay? So if something runs through this curve, okay, something runs through this curve at the minimum, okay, it's going to be going, say, with speed v, and its y, its acceleration in y direction is going to be d squared over r. So that ties all these things together very nicely. So that's the curvature. This is true at the local minimum, the way we've constructed it here. And the way we could show that is we would have, so I'll go ahead and erase this now. Hold that. We can use that there. Suppose we had x of t and y of t, right? So x of t, actually let's do this. So we would have x of t, v sub x of t, y of t, v sub y of t. As we traverse this curve here. So right at the bottom, when we're in that local curvature there, we would have d squared y dt squared, because y goes as x squared, would give us exactly this v squared over r. So I'm going to leave it at that. Possibly next Monday we'll turn this into a little homework assignment as well. We could actually, maybe I should pursue this exactly. Right now it's a little bit late to get too deep into it, but that's the idea. In fact, actually, let me do one more thing here. So we found this, so what we have is, if we're going to call this now y of x for this curve, we have y of x equals 1/2 1 over r x squared at and around the minimum. Okay. That's what we've shown, you know, by way of Taylor series. Essentially, that's the second term there. And that's where we take the derivatives here. First one gonna kill this, second one's gonna give us b squared over r. Okay. Good, so I'm gonna leave it at that for now. That's a good point. And we can do a little more uniform circular motion as well before we launch into Newton's law and solving differential equations. Okay, that'll do it for today.